Okay. Oh, I guess it would help if I actually showed this on the.
I mean, just maybe.
Probably. My brother said you were in a band. Is this true?
What kind of a band?
I don't remember.
You was in the band.
I was in a Jimmy Buffett cover band.
I have no idea what that means, but all right.
A band that covers Jimmy Buffett songs. That does covers of Jimmy Buffett songs.
Sounds like fun.
I could have been a rock star. But I chose to educate young minds instead.
Both important.
Okay, so we started talking about partial pressures of gas. And we said that if we have a mixture of gases, each gas behaves as if it's the only gas that's present, and we can determine the behavior of each component of the mixture separately. And we made the statement that the total pressure was going to equal the partial pressures. And so this term partial pressure makes a lot of sense. It's partial meaning it's part of the total. And we said that we can do a variety of things to look at this in different ways. We can say that the total is the sum of the partial pressures, and we can say that the pressure, that partial pressure, is equal to the number of moles times RT over V for that particular thing. And we could factor out the numbers of moles if we wanted to, and say that we could come up with a total by adding the number of moles together and then plugging that into the gas formula. Oops. Didn't mean to do that. And then we did an interesting problem. And there's another sort of nebulous concept that's related to this. It should make sense that if the total pressure is due to the number of moles in a sample of gas, that I can determine what the partial pressure is by determining the ratio of the number of moles of that gas to the total number of moles. Okay, so if I have let's say if I have 5 out of 12 is A, and 3 out of 12 is B, and 4 out of 12 is C, hopefully it would make sense that my partial pressures would also use these ratios here as far as whatever the ratio of the partial pressures was. Okay, so if the total pressure is due to the total number of moles, the partial pressure of any gas is due to the mole fraction of that gas. We're going to call this the mole fraction. Okay, so this is the mole fraction. How many moles out of the total does this one gas have? And we symbolize that with a special character, the Greek letter chi. So this is the symbol that we use for that. Did I start that? Okay. And so we could say that if the pressure, the total pressure equals the total number of moles of gas times RT, the partial pressure is due to the mole fraction of that gas. Okay. And I can say that because these things are going to be constant, right? If I say that the pressure is due to the total number of, or the partial number of moles, I could say that whatever that mole fraction is, NA over N total, If I multiply that times the total pressure, I should get the partial pressure. Okay? So this leads us to another relationship that's important. The mole fraction, in other words, NA over N total, is the same thing as the ratio of the partial pressures. Okay? So we can work some problems with this, and we'll talk about the significance of this relationship in just a second. The partial pressure of oxygen was observed to be 156 torr in air with a total atmospheric pressure of 743 torr. Calculate the mole fraction present. Since we know that the mole fraction is the, and let's use oxygen here. So the mole fraction of oxygen, the number of moles of oxygen over the total, equals the partial pressure of oxygen over the total. This is going to equal 156 torr over 743 torr. And I forgot what it was. So 0.209. So the mole fraction is 0.209. How does that jive with what you know about the percentage of oxygen that's in the atmosphere? What do you know that the percentage of oxygen in the atmosphere is? You should all know this.
Is it like 21%?
It's about 20%. Okay, 2080 is a good general number. So this is, that fraction is a correct fraction. Okay, so notice that we're using torr here. We're not converting that to atmospheres because all we're really worried about here is the ratio, right? I don't really need to know anything about the gas laws or anything that relates to the gas laws, so I don't need this in atmospheres. I just need to know that this ratio of particles and the ratio of partial pressures is the same. The ratio of the number of moles of particles and the ratio of the partial pressures is the same. And again, that's all because of the PV equals nRT thing. The total number of particles, the total number of moles, or the total number of the total amount of pressure and the total amount of particles is the ratio of these things is going to be equal to each other. So we're assuming though that volume and temperature are constant when we're making that statement. Now here's why this is important. Okay, because the partial pressure of a gas reflects the mole fraction of the gas, and in fact it's the same thing, that ratio of the partial pressure to the total pressure is the same thing as the mole fraction, the ratio of moles of one particle to the total particles. We can use this knowledge of partial pressures before and after a reaction occurs to determine reaction stoichiometry. Okay, if volume and temperature are constant, the number of moles can be used interchangeably with the partial pressure. Okay, if volume and temperature are constant, the ratio of the moles to the total can be substituted for the ratio of the pressure of A to the total pressure. Okay, so I can use this to help me determine reaction stoichiometry. And this is really a seriously difficult problem, this problem here. Xenon and fluorine will react to form binary compounds. What's a binary compound?
It has 2 parts to the compound.
Yeah, so compounds that have xenon and fluorine in it, right? So we don't know what the subscripts are yet, but we're going to use our understanding of mole fractions and partial pressures to help us out here. Again, remember, Na over N total equals Pa over P total. Okay, so we're going to put xenon and fluorine into a reaction vessel. This is a nickel reaction vessel. The nickel won't react with anything that's in the vessel. It tends not to react very much. And we're heating it to 400 degrees Celsius. And that will cause xenon to react with fluorine. We have to heat things to a pretty high temperature to get xenon to react with anything. It's a noble gas, right? And it doesn't really want to react. So if I'm going to get it to combine with something else, I'm going to have to put a lot of energy into it to cause it to happen. So a 100 milliliter nickel container is filled with xenon and fluorine. Okay, and so I know that my partial pressure of xenon in this vessel is 1.24 atmospheres. And I know that the partial pressure of fluorine, that's F2, is 10.10 atmospheres. Okay? And what I have said is that because we're going to say that my starting and ending conditions are going to be the same, and we'll see that here in just a second, I said because of that, I could treat these as if they're a number of moles instead of atmospheres. Okay? I can literally say that's the same thing as the number of moles. Okay, so what we're going to do is we're going to put these two gases into this container at a temperature of 25 degrees. And when I put those two gases and I measure the partial pressures of each gas, I find out that the partial pressure of the xenon is 1.24 atmospheres and the partial pressure of the fluorine is 10.10 atmospheres. So I can literally pretend that these are numbers of moles. Okay? The reaction vessel is then heated to 400 degrees to cause the reaction to occur, and then is cooled to a temperature at which fluorine is still a gas, but the xenon is going to be a non-volatile solid. Okay? And at this point, we're not finished transferring things yet. But what I've basically done is I've said I have caused this compound to drop out of the mixture. It's no longer a gas because I cooled it. And the rest of what's left is fluorine. And I can take that fluorine and then I can put it at the same condition that I had originally. I can put it back into a different 100 milliliter container at 25 degrees Celsius. So it's as if I haven't changed the circumstances. Okay? Whatever fluorine gas is left is at the same condition that it was when I first put the fluorine and the xenon in the reaction container. It doesn't matter that I've in the meantime heated those two gases to 400 degrees and I've caused the xenon fluoride compound to solidify. It doesn't matter that I've done all that. I've taken this gas and I've put it back at the same conditions. So what I've said, the remaining gas is transferred to another 100 milliliter nickel container where the pressure of F2 gas at 25 degrees is now 7.62 atmospheres. Okay? So, assuming all the xenon has reacted, what is the formula of the product? Okay, so it's as if I started with 10.10 moles of fluorine and 1.24 moles of xenon. And if I keep the conditions the same, now I have a pressure of fluorine gas at 7.62. Okay, 7.62 atmospheres, and we'll cross that out and say at 7.62 moles. Okay, so it's as if I reacted how many moles of fluorine with, and this is all gone now, right? I don't have any more xenon gas, so I used that 1.24 moles of fluorine. How many moles of xenon, how many moles of fluorine did I use in comparison? Okay, so if I still have this many moles left, I must have used 2.48 moles, right? Okay, so the compound that I had to have come up with then had 1 mole of xenon, or 1.24 moles of xenon, compared to 2.48 moles of fluorine. Okay, so be careful here. You can't then say that the formula is ZeF2, because how many atoms of fluorine do I have for each mole? I have 2 atoms of fluorine for each mole, right? So I have 4 times the number of fluorine atoms as I do xenon atoms. So the formula would be xenon F4. Okay, and since these are all non-metals here, I would say that that's xenon tetrafluoride. Okay, so this is how we could use the knowledge that partial pressures reflect mole fractions to look at stoichiometry. I can figure out what the reaction stoichiometry is based on the partial pressures, which are, oh, by the way, similar to the mole ratios. Okay? So if you don't know the story there, that's a seriously difficult problem. There's no way you could actually figure that out. Okay, another application of partial pressures is collecting samples of gas in water or over water. So we could collect samples of water insoluble gases by bubbling them through water and trapping them in the end of an inverted tube, which is what we did in our lab, right? Hydrogen is basically insoluble in water, and so none of the hydrogen that we created stayed in the water, right? It all came out and created that volume of hydrogen gas that we have. But what we said the problem is that water vapor particles also enter the mixture, and so wherever we have that situation where we've collected a gas over water, some of those particles are going to end up being water vapor, right? So I have to subtract that as far as the partial pressure goes, and because of that, I can also subtract that as far as the number of moles goes. Okay, so I could say that whatever the partial pressure is related to that, I'm also going to subtract out a corresponding number of moles. So the thing about this is that this has been looked at for a long time, and we have references that tell us at certain temperatures a certain amount of water vapor is in the atmosphere. So vapor pressure of water has been determined for a range of temperatures, so we can look up the vapor pressure for whatever the temperature of a lab happens to be. And we can equate the pressure of the collected gas with the atmospheric pressure by placing the inverted tube into a large graduated cylinder and adjusting the water level in the inverted tube so it's similar to that in the cylinder. And at this point, the pressure of the gas has to equal the atmospheric pressure. Remember, again, I've got this cylinder of water here, and I've put my Untitled into this. And if my water level in the tube, in the Untitled, is equal to the water level in the graduated cylinder, then since atmospheric pressure is pushing on this, that must mean atmospheric pressure is also pushing inside this tube here. Okay, so if these levels are equal, then the pressure inside this tube has to be the same as the pressure pushing down on the pool of water inside the graduated cylinder. Okay, so at this point, the pressure of the gas would equal the atmospheric pressure, and the volume reading at this point is the volume of the gas plus the water vapor. Okay, so we can remove the water vapor from the equation and then say the rest of the volume is related to the gas. So a sample of solid potassium chloride was heated in a test tube and decomposed by the following reaction. And that reaction's down here. Let me rewrite that in here so you can see that. 2KClO3. So what's the name of this compound?
Potassium chloride? No.
Remember the version of the ClO ion with 3 oxygens is the ATE form. ClO4 would be perchlorate, ClO2 would be chlorite, and ClO would be hypochlorite, right? So this is potassium chlorate, okay? And all we're doing, it's going to be on the side of the equation by itself. It's the only reactant. So when I see that there's just one reactant, I have to call this a decomposition reaction. Okay, I have to call it a decomposition reaction. And potassium chlorate, chlorates decompose into the chloride, KCl, and oxygen. Okay, they decompose into the chloride and oxygen, but this isn't balanced. I've got 2 KCl, so I can put 2 in front of that. And I've got 6 oxygens here, so I need to put 3 oxygens there. So this is the reaction that I'm going to have, and this is very similar to what we did with the magnesium and the hydrochloric acid, in which we created magnesium chloride and hydrogen gas. Okay, and so that's going to have to be a 2 there. And we released the hydrogen gas, except in this case, this was a single replacement reaction, right? We replaced the hydrogen with the magnesium, and we released the hydrogen gas. Here, we're releasing the oxygen gas. And in this case, what's important about this relationship is that for every 3 oxygen molecules, I started with 2 molecules of KClO3. So the mole ratio here is 2 to 3. So I started with 2/3 of the number of moles as the moles of oxygen. So if I know the number of moles of oxygen that I got in this reaction, if I know the number of moles I got in this reaction, 2/3 of that number of moles would be the number of moles of KClO3. And once I know the number of moles of KClO3, I also know the number of grams, right? Okay, so the way that we can think about this, we want to, first of all, calculate the partial pressure of oxygen in the gas collected, and we want to figure out what the mass of the KClO3 in the sample was that was decomposed. How much of this did I start with? Okay, so calculating the partial pressure of oxygen in the gas, I know that the total pressure equals the partial pressure of the oxygen plus the partial pressure of the water. I've been told that the total pressure, which we've equilibrated to the atmosphere, we were told that the atmospheric pressure is 754 torr, okay, or 754 millimeters, right? Millimeters and torr are going to be the same thing. So if I wanted, I could say that that's 754 millimeters or instead of torr. But I know that that's going to be related to the total, or the pressure of the oxygen plus the pressure of the water. And so if I want to know what the pressure of the oxygen is, PO is going to equal P total minus P water. That sounds weird, doesn't it? P water equals 754 torr minus, and I've been told at 22 degrees Celsius, which is where this happened, the water vapor pressure is 21 torr. So that means that the pressure of oxygen is 733 torr. Okay, now my solution to this gets that part right. But I just realized when I was reviewing this that I screwed up the calculation of the number of grams. And we'll see if you can figure out what I screwed up here. So we know, and the first thing that you're going to ask when you want to find a number of grams is, do I know a formula that will find a number of grams? You only know one formula that finds number of grams. So you don't even have to think about how to work this problem. You know how to start because you know that grams equals moles times molar mass, okay? So if you write that down, you don't even have to think. You go, oh, I need to find the number of moles of KClO3. I need to find the number of moles of KClO3. Okay, and here's where I screwed up. I want to find the number of moles of KClO3. And what I did was I just said the number of moles of KClO3 is going to equal PV over RT, which is not right. I left out something. I left out the fact that this is 2/3 times the moles of O2. Okay? I forgot to look at my equation and say, oh, I need to say that this number of moles is 2/3 of this number of moles. Okay? And that's what I have to set equal to PV over RT. Okay? I forgot to say that this is equal to 2/3 of the number of moles of oxygen. Okay? So equals 2/3 times the moles of oxygen is what's going to be equal to PV over RT. Because it's not the moles of KClO3 that's causing the pressure, in the tube, right? It's the oxygen that's causing the pressure. So I can find the number of moles of oxygen by equating the number of moles of oxygen to PV over RT. And so that pressure we said was 733 torr, but for this to work, I need atmospheres, right? So 733 atmospheres, I know I have to divide that by 760 to convert that to atmospheres. Okay, and the volume we were told was 0.650 liters. Okay, I don't know why I put that under, let me erase that, times 0.650 liters, and then 0.08206 liter atmospheres per mole Kelvin times 295 degrees Kelvin. And if I want, I can go through. I know that that's atmospheres and that's atmospheres. I know that's liters and that's liters. And I know that's Kelvin and that's Kelvin. And that's going to leave me with 1 over moles, which is the same thing as moles, which is what I want. So I have 0.0259 moles of oxygen. Okay, and I have to multiply that by 2/3. Okay, so then I should have had the point, I should have said grams of KClO3 equals 2/3 times moles times molar mass. And if I did that, I would get 2/3 times that number. So what's 2/3 times 3.17? So 2.11 grams is the correct answer. Okay. So that gave me an opportunity to show you what a mistake in a problem like this might look like. Okay. I should not have used moles times molar mass here. I should have used 2/3 times moles of oxygen times molar mass. Any questions about that? Okay, so we've seen how partial pressure can be used in 2 different applications. We saw how we could use it to help us find stoichiometry. Okay, before I did this, I didn't know how many moles of fluorine 2 would react with that many moles of xenon. But when I found out that the partial pressure decreased from 10.10 atmospheres to 7.62 atmospheres, that's the same thing as saying I used that many moles of fluorine or F2 to react with this many moles of, now I didn't use that many moles, okay? I could just substitute the number of atmospheres for moles to find that ratio. And then we also use this in collecting gases over water problems. Any questions about that? This gas law stuff is pretty complicated, isn't it? But it's stuff we have to understand. This next part is a little bit more conceptual. So we've talked about this before. We've said that the whole thing of the gas laws was kind of the key or pivotal type of investigation that led to us understanding that everything is made up of particles. Because the gas laws don't work if gases aren't made up of particles, right? And if these gases are made up of particles, but then I cool them down to liquids or solids, it would still make sense. Well, the liquids and the solids must still be made up of particles, so all I'm really doing is just slowing the particles down so that they take on a different form, physical form, when the forces between the particles get stronger and stronger, right? When I decrease the amount of energy that these particles have, their forces of attraction for each other start to exert themselves, and at some point I create this cohesiveness that allows me to have a liquid, but it's not locked into a rigid crystalline structure. It's just cohesive enough to be liquid. But then I cool it down further, and eventually I get to the point where these particles are kind of locked into this rigid crystalline structure. No matter what it is, I have this rigid crystalline structure. Now, you are aware that there are some solids that don't really have this rigid of a structure. For example, butter doesn't have a rigid, I can squeeze it, or wax, or even glass flows. You may not be aware of it, but glass actually flows. How do I know that? What real-world observation allows me to know that glass flows? If I have a pane of glass here, what happens to windows over time if I just leave a window sit and sit and sit and sit?
It won't be able to
If I have the wood frame, it won't be able to what?
open or close.
Yeah. Yeah, because the glass, if I have it in this wood frame here, will flow to the point where it'll spread out at the bottom, and it will force the wood frame to be tightly held into the window frame. So that's why it won't open anymore. It's not because the paint sticks or anything, although it could be if you shut the window after you'd freshly painted it. But in general, windows stick in their window frames because over time the glass actually flows and it spreads out at the bottom of the pane and forces the window frame to get stuck in the pane of glass frame to get stuck in the window frame. Anyway, I've got this theory that I have particles or molecules, that's what the molecule part is, particles in motion theory. They're particles in motion in theory is an attempt to explain the behavior of the gases as modeled by the ideal gas law. So it's not enough for us to know that PV equals nRT. That's just an observation. We just created this law that describes the behavior of gases. This is a mathematical relationship that describes the behavior of gases, but it doesn't say why the gases have that behavior. It just says the gases have this behavior. But if we analyze the average motions of large numbers of particles in gases, we find out that the features of the gas laws depend on our understanding of the amount of energy that's in the particles. Okay? So, particles in motion in gases follow rules of classical mechanics, classical physics. They have defined masses, and they are in random motion with a range of velocities. Okay, so if I have a particle that's in motion, it has a velocity, right? Okay, and generally we're going to put velocity in meters per second. Velocity equals meters per second. Okay, now for the most part, these particles are going to travel in straight lines, so we can use actually very simple physics to describe the motion of these particles. Okay, but we don't want to just describe the motion of one particle. One particle isn't going to do us a whole lot when we're trying to analyze the behavior of particles. Okay, we recognize that if I have a mole of particles, a mole of gas, and a mole of gas takes up how many liters? What was our molar volume? At standard temperature and pressure?
Was it centimeters cubed? No.
1 mole of gas takes up 22.4 liters. Okay, that's a quantity that you would be given on the AP test, although you should know it. The molar volume at standard temperature and pressure of any gas, of any ideal gas, is 22.4 liters. Okay, but if I have one of these, I have 6.022 times 10 to the 23rd particles, and that's like 600 sextillion particles. Okay, and every single one of these particles is following the rules of physics. Okay, because they are in motion, they have a specific kinetic energy. Each particle has a kinetic energy of 1/2 mv squared. Okay, now the thing is, not all of these 6.022 times 10 to the 23rd particles are going to have the same velocity. For simplicity's sake, we're going to say they have the same mass at this point, but they're not all going to have the same velocity because they're smacking the sides of the container, and they're smacking other particles, and they're constantly transferring some of their kinetic energy to other particles, and other particles are smacking into them and constantly transferring energy to those particles. But at a specific temperature, and let's say at 273 degrees Kelvin, or we could say 295 degrees or 98 degrees Kelvin, if we wanted to say it was like room temperature. At one of these temperatures, I have an average amount of kinetic energy for all of these particles, and that temperature will always have that particular average kinetic energy. Okay? I could have lots of particles at different kinetic energies, but the average will always be the same at a specific temperature. At this specific temperature, the average kinetic energy of all of these particles will be greater by a certain amount. Okay? And we can relate pressure and volume and temperature to the amount of kinetic energy. Okay? And that's where we get the explanation for why all of these values, these behaviors are observed the way they are, because they're linked to the specific amount of kinetic energy that these particles have. If I increase the temperature, I increase the kinetic energy, and that's going to increase the pressure, and if my container can change sizes, that would increase the volume as well. Okay? So all of these things, the number of particles times the amount of kinetic energy in each particle is going to be proportional to the pressure and the temperature and the volume. These give rise to predictable pressures and volumes. So we have to assume some things when we talk about this. We have to assume that the particles are so small compared with the distances between them that the volume of the particles can be assumed to be negligible. Okay, so when I'm doing all my gas law stuff, I have a container here, and it's got all my particles in it. It's got all my particles in it. We're assuming that if I compressed all of these particles down into a tiny volume, that it wouldn't be a significant part of this whole volume. Okay? Because if these particles took up a significant part of this volume, that's going to screw up my observations. It's going to screw up the volume part of my gas laws. Okay? Now, if I happen to have really, really high pressures and really small volumes, or if I have really high numbers of particles, then that's going to cause some aberrant behavior, and that's when we'll start to think about non-ideal circumstances. So we're going to have to consider non-ideal circumstances in a little bit. But for now, as far as the ideal gas law goes, we have to assume that the amount of volume that these particles takes up is negligible. We also have to assume particles are in constant motion, and because they have mass, they have kinetic energy. That's correct. The average kinetic energy of a collection of particles is assumed to be directly proportional to the absolute temperature of the gas. And remember, this is where it came in, that it doesn't matter what the mass of the particles are, it doesn't matter what type of particle it is, because if I increase the mass, the velocity will decrease, and I'll still have the same amount of kinetic energy at a certain temperature. So if my temperature is 273, and I have a certain number of joules of kinetic energy, I have a certain number of joules, let's say I just have 100 joules of kinetic energy in my total sample. If I changed the mass, if I increased the mass, the velocity of those particles would slow down so that I would still have that same 100 joules of energy. Okay? So, doesn't matter what type of particles are present, the average kinetic energy of a population of particles is the same at constant temperature regardless of the type of particle. To what variable of the gas law is the amount of kinetic energy related? So which of these three variables, pressure, volume, or temperature, which of these three variables are we relating the kinetic energy to? Which of these three variables is going to cause the increase or decrease in kinetic energy?
Would it be temperature?
Yeah, temperature. If I increase the temperature, I increase the kinetic energy. If I decrease the temperature, I decrease the kinetic energy. Okay? Particle forces. The particles are assumed to exert no forces on each other. They are assumed neither to attract each other nor to repel each other. Under what circumstances will interparticle forces come into play, and what variables of the gas law would this specifically affect? Okay? When is it that interparticle forces start to become exerted? Remember, we said in gases, we assume that there are no interparticle forces. But under what circumstances will forces of attraction between particles start to come into play? And remember what kind of properties we associate interparticle forces with, not intraparticle forces. Do we associate interparticle forces with physical properties or physical changes or chemical properties?
Isn't it?
So when I think about inter versus intraparticle forces, my brain should go to the water molecule. Okay? Because if I have two water particles, remember, because of their polarity, I'm going to exert a force of attraction between the negative part of this one and the positive part of this one. This is an interparticle force, right? It's between the particles. Therefore, if I strengthen these forces, if I slow these particles down enough where these interparticle forces are start to be felt, I'll turn it into a liquid. And if I strengthen them even further by slowing them down, I'm going to turn it into a solid. Okay? If, on the other hand, I break one of these bonds, I change the chemical properties of it, right? Okay, so when you think inter versus intraparticle forces, your brain goes to water molecules, and you have this model just built right away for you to remind you, hey, if I break these bonds, or if I affect these bonds, I'm affecting the physical properties of water, solid, liquid, gas. If I break these bonds, I'm affecting the chemical properties of water. Okay? So particles are assumed to exert so the kind of forces that we're talking about here are these interparticle forces, right? The forces between these particles as far as gas particles go. So if we're gas particles, we're assuming that these forces are non-existent because they're moving so fast that they don't have time to attract each other. And they're so far apart, they don't have the ability to attract each other. Even when they smack each other, they don't affect each other because they're going too fast. Okay? But if I slow these things down, under what circumstances will interparticle forces come into play? If I slow them down, in other words, if I decrease the temperature, or if I push them too close together. Even if there's a lot of energy, even if the temperature is fairly high, maybe I can compress them to the point that they're going to be close enough that they'll start to feel the interparticle forces. So under what circumstances will these come into play? If I have decreased volume or increased pressure or decreased temperature, these can come into play. And the variables that this is going to affect, the variable that this is going to affect mainly is if I have a particle here and it's headed towards this wall where it's going to exert pressure, and I have another particle here that's grabbing onto this particle and slowing it down, what's that going to do to the pressure?
It's going to reduce the pressure.
It's going to reduce the pressure, right? You're not going to smack that side of the container as hard as you did before because I'm slowing you down because I'm exerting my force on you. So I'm going to especially affect the pressure. As the particles have kinetic energy, when the particle strikes something, they exert force. Collisions with the wall of the container or each other are considered to be perfectly elastic. If I smack this wall, in contrast to what I notice in the world around me, I don't lose energy in the process. Okay? If I throw a rubber ball up against the wall, when I hit that wall, that rubber ball flattens out. Okay? I use some energy to cause that ball to flatten out. Okay? Now, theoretically, I could return all of that energy to the ball and its kinetic energy by this being perfectly elastic, okay? If it rebounds to exactly the same degree, or it expands back out to exactly the same degree that it was compressed by, then all of that kinetic energy will be returned to the ball. But what's going to happen is that as this ball smacks the wall, some of the particles in the ball are going to be speeded up, okay? And so some of that kinetic energy is going to be lost in the smacking of the wall. Gas particles don't do that. When they smack each other or they smack a container, they don't lose any energy. They're perfectly elastic. Okay? So those are the assumptions of this theory, and this was created primarily in the late 1800s. James Clerk Maxwell, probably the greatest living theoretical physicist of all time, even considering Einstein. They're both in the class by themselves. And another guy named Ludwig Boltzmann, although many investigators who are not well remembered contributed greatly before this. The math involved in the development of this theory is beyond the class, so most of this is conceptual, thankfully. So how does this kinetic molecular theory explain the relationship of pressure to volume at constant temperature and number of particles? So remember, we have our ABCs, and this is number of particles, and this is pressure and temperature, right? Okay, so the relationship of pressure to volume, okay, change in volume means particles will hit the walls of the container more or less frequently. Okay, so if I change the volume, if I make my volume smaller, that's going to increase my pressure because particles are going to smack the wall more frequently. If I expand the volume, that's going to decrease the pressure because the particles will smack the wall less frequently. So the place that something like this might come up is in if you might be asked to explain an observation related to the kinetic molecular theory. Relationship of pressure to temperature and constant volume and number of particles. This was Amundsen's law, which we don't really have to pay attention to, but in case we thought about it, the relationship of pressure to temperature, that should be pretty obvious. If I change the temperature, that's going to increase the kinetic energy, and that will increase the force with which the particles hit the wall of the container. Okay, so once I understand what I'm asking here, these are pretty obvious pieces of concept, right? If I increase the kinetic energy, I'm going to increase the pressure, right? Relationship of temperature to volume at constant pressure and number of particles. Change in temperature will increase the kinetic energy and the force the particles exert, requiring a corresponding change in volume to maintain constant pressure, right? If I smack the walls of my container with greater force, if I'm going to keep a constant pressure in there, I'm going to have to expand my volume, right? And the sort of apparatus that you would use in a situation like this is a cylinder that has a piston that floats up and down with change in pressure. So, and again, we would recognize that I have the same pressure in the end as in the beginning by thinking about this as being an open container, and if I increase the temperature in here, that's going to initially increase the pressure, but that increase in pressure is going to push the piston up, until that pressure is once again equal to atmospheric pressure, okay? And so by saying constant pressure, oftentimes we're meaning that I have an apparatus that's exposed to atmospheric pressure, and I can say that I've got a constant pressure here because, and this is always something that confused me. It always made me just nuts because it's like, well, wait a minute, you don't have a constant pressure. Well, they don't mean that you have a constant pressure throughout the entire process. They mean you have a constant pressure at the beginning and the end of the process. Okay? So always keep that in mind. Relationship of number of particles to volume at a constant temperature and pressure. If I increase the number of particles and I have the temperature and pressure the same, I'm going to have to increase the volume to accommodate the different number of particles to maintain that constant pressure. So it's kind of the same thing, except in this case, I'm increasing the temperature. In this case, I'm increasing the number of particles. And then the law of partial pressures states the total pressure is equal to the partial pressures based only on the number of particles. Kinetic molecular theory predicts this as it states that all particles are independent of each other, and the nature of particles is not important. So I can segregate the particles that I'm talking about because it doesn't matter whether they're hydrogen or oxygen or nitrogen particles. I can segregate them, and I can say that each one of these exerts a partial pressure based on its number of particles. Okay? I am going to stop there because that's a lot of stuff to digest. Okay? Next time, we will finish, that's Friday. Next time we'll finish talking about gases by finishing talking about kinetic molecular theory and talking about non-ideal gases. And then we'll conduct a review, and then we'll have to have some kind of an assessment. It'll probably be a take-home test, okay? Because I don't really want to take in class time to take tests. But we will have to have some kind of an assessment on this. And then we'll start talking about atomic theory, the structure of atoms. Okay.